Okay, so I think we are wrapping up chapter 13. However, if you take a look, if I recall this right, I believe this is 2 days of work here. So our exam, I will be talking about this stuff on Monday, and then I'm pretty sure this is Wednesday, so our exam will be Friday of this week. Exam over this chapter 13. And notice that there's no concept preview, so that following Monday, right away, boom, we start on chapter 14. So make sure you have the bold words there for Monday. Okay, so that's the game plan. Let's see how it works out. So just looking at their notation, you see we have these little j, little l, little s, angular and spin orbit and total momenta, angular momenta quantum numbers, but they're smaller case. And then if you go down further, what we're going to be talking about later on, they turn them into capital L, right, and capital S, and capital J. So what this is just a single electron. And then we're going to start talking about multi-electrons and coupling them using our Clebsch-Gordon rules that we practiced on. Okay, so there's just a lot of terminology and some things we should get used to. And we're starting out with Singlet. So they don't really take things in order, but that's okay. I mean, so Singlet, we're going to be doing some coupling to figure out what these total momenta are. And like this is spin momenta. And if S is 0, we'll figure out how we get it to be 0, but then 2s plus 1 is just 1. They call that a triplet, right? But if S is, right, S is 0. But if a triplet, S would be 1, okay? They call this the multiplicity, and that's just their terminology here. But S equals 0 means literally that the total spin angular momentum is 0. And remember how they get this stuff. They take the square root of whatever that symbol is, right? So if S is 0, you'd have S times S plus 1, right? So that's where this is kind of coming from. Okay. All right. So remember, this is just their way of writing the magnitude of angular momentum. And we have, just to be clear, we have 3 that we're worried about: J, L, and S. So S is the spin angular momentum, right? L was the orbital angular momentum. And J is the total angular momentum. So if you want to get the magnitude of any one of these, right, we'll just plug them into our expression to get magnitude, right, the square root times h bar. Okay. So what they're trying to get at is that, now notice, again, these are smaller case, bless you, smaller case, so that means we're worried about how many electrons here? Just 1, right. So you think if there's just 1, there wouldn't be anything to couple, right? Because what are you going to couple? There's only 1 electron. But take a look. I mean, if you have this 1 electron, right, it'll have a number. You can put a little subscript on there, right? It'll have a number for all these guys. And here's how we're going to calculate the energy. Right? Just given the J, the L, and S for that 1 electron. H, Planck's constant, C, speed of light. A is the spin-orbit coupling constant, so it's just going to be a number. But what what they're trying to illustrate here is, man, even though you have one electron, these energies are split. That it's like two magnets. This is supposed to be the little L, right? That's supposed to be the little S. So it's a charge. It's moving. You have they turn into little magnets. Is what you want to think about. And how could you align these magnets, right? One for L, one for S, so that in one case it's higher energy, the other case it's lower energy. Can you see how they're trying to illustrate this? Why would one be a higher energy? Think of them as little magnets. Right? What's going on with the arrows? The higher energy. They're both pointing in the same direction. So they could both be pointing up or pointing down. It doesn't matter. But when you're supposed to think of a magnet, we're not used to drawing arrows. We're used to drawing what at the poles? What would we put up here? Well, more for dipoles. I think for magnets, don't we write N and north and south, right? Because of the compasses and stuff. I guess that's the convention. So if they're both pointed up, how would these two magnets be aligned? That's one. Oh, I guess the other one's a lot smaller. How would this other magnet be aligned? Same way, north and south. So it's higher energy, right? Here they're attraction for lower energy. So that's why they're saying that even though you have one electron, this orbital and this spin angular momenta, they're acting like little magnets, and they can be, there's two possibilities here. You think there'd be a lot more than two possibilities because they can orient, right? But no, remember it's a microscopic world, so energy's quantized. There's only two possibilities. But those two possibilities result in split energy levels. And all of that is referred to as spin-orbit coupling. Okay, all that's referred to as spin-orbit coupling. Again, how many electrons are we worried about here? Just one. And life is already getting complicated. Okay. So then we drew these things, I think, in the last chapter. Started with a P. Pablo, what do we call them? Projections, right? And so it looks like L is 2, S is a half. If little l is 2, what hydrogenic atomic orbital is that supposed to be in? What do we call it? If little l is 2, that would be a what electron? A d electron, right? So this would be D1. Now it could be 3D1, 4D1, whatever, right? But we just know that it's a d electron for these projections. And the only reason why I know that is because I see L equals 2, and it's a little l, so that means there's only one electron. And there's one electron, so S is a half. And what they're doing is, how did they get the 5 halves and the 3 halves, though? Right. Now, a couple hints. One, what's that? The one hint is J is the total angular momentum, L is orbital, S is spin. So you have to add them up, right? But we have to couple them. So we have to follow our rules for coupling. And remember, that was the sum all the way down to their difference. Now, if you want an equation, L plus S, yeah, here it is. Now, this is uglier than what we need, but, right, there's L plus S down to L minus S, but pretty much there's some. Remember, we write the sum all the way down to their difference and fill in everything in between? So if you have L is 2, and what? Little s is a half. You couple those, my J would go from 2 doesn't really help, so write it as 4 over 2. So 4 over 2 plus a half would be 5 over 2. And then, and then down to their difference. So 4 over 2 minus a half would be 3 over 2. Okay, is there anything in between, Ashley? Because intervals are 1. No. So we just have 2 possible J's. So then that's why they just have 2 possible J's there. Now, Brad, do you remember if they said draw it to scale? What would you have to do? You do everything the same, but you have to do something with your ruler. Yeah, yeah. So like both of these would be drawn this way. But I guess what I'm getting is, how do you draw the length of these arrows? Yeah, it's this equation. All right. So you just end up. It's easiest to do it in centimeters or something. I'm not sure, but that's how we did it. That's how they have the length of these arrows.
And each one of those origins or vector origins gets set to the origin on your CY graph.
Yeah.
Or CX graph.
Okay. Okay, so a little review. I don't think they're going to have you do that, but just to see if you remember that stuff. Okay. So we kind of skipped over this on this equation, though, that it looks like you would have the lowest energy with, right? How would you get the lowest energy with JLS, right? Would you want big or small numbers for this? If you want the lowest energy, you'd want just looking at that, what you're subtracting and what you're adding. You want J to be this little J number. You want to get the smallest energy possible, according to this expression. You'd want J to be small or big? Small, right? Because then you get smaller numbers. How about L? Big. And S to be big, right? So, all right, so small, big, big, okay.
This is to have small energy, right?
Yeah, to have small energy. Except that's too much of a generalization. We really got to be coupling. So the story is really more complicated than that. I mean, this is where it makes sense to me. But then all of a sudden, if you say this is for shells that are less than half full. What's a shell? What's a shell?
Energy level.
Right? Do you remember when we called? Yeah, it's kind of pretty much the energy level. Like if I don't know, like if you have 3D5, that would be half full. Yeah, half full. So 3D2 would be less than half full, right? So everything makes sense to me when things are less than half full. And then we just look at the equation and say the answers, right? Small j, big L, and big S. But when they're more than half full, the big L and big S makes sense, but now they want big J to get the lowest energy. Large J. So that's just an oddball thing. I don't know if that's going to be brought out in the homework or not. I don't remember. But I just want to tell you all this stuff. Okay. So spin orbit coupling. So if you're going to have, this is going to work, right? You have to have some orbit coupling, otherwise this whole thing isn't going to, otherwise you aren't going to have any spin orbit coupling. So little l can't be 0. Now when is little l 0? If you're a what electron in a what orbital? S. Yeah. Then there wouldn't be any spin-orbit coupling because there isn't any orbital angular momentum.
Is that why it's like the only orbital is a sphere?
Um, I think the shape of these orbitals more has to do with standing waves, and the more shape you have, right, the more nodes that you have, the more angular nodes that you have, and
Looks like some of those orbitals look pretty.
but you're right in the sense that L is the number of angular nodes, so it is an interesting thought. I haven't really thought about that, but I don't think so. It's hard to make these macroscopic generalizations to this quantum world because it operates in such weird physics that you can't relate to. So it's hard to draw your finger and make correlations. Okay, a level. So this is terminology we just need to get used to. Level. And what we haven't written any yet, but we're going to be writing term symbols. And like I said, they're kind of doing this out of order, but that's okay. We're going to be writing term symbols. And that was our big goal for this entire chapter, because if we can write term symbols, and then we can look at the term symbols and we can determine ground state. It's just instead of electron configuration, right? We can determine transitions, all that kind of stuff. Well, when you start writing these term symbols, they like to refer to the word level. And those are all the term symbols that have the same J. Term symbols. Okay. Now I'm writing capital J because we're going to get out of this one electron thing pretty quick here. Okay. The number of, just going to give you this right off the bat too, the number of different states, right, for a level is the number of m sub j values. So there's two ideas for level. One is that it's determined by the value of the total angular momentum, J, and the number of different states in a level is the number of m sub j values. Okay. So in this figure, they're trying to say, okay, we only have one electron, so that's why they're still using the smaller case letters, and they're saying that it's a p electron. So little l would be, what would the little l be if you have a 2p1? It has to be 1. S would be, it's a little, S would be a half, right? So how did they get, and again, you have to sum down to their difference. So that's how they get the 3/2 and the 1/2. But I wanted to make sure that we can see how they get these two, the actual energies, right? So that you have an electron, only one electron, and it's 2p1. I mean, life should be simple, pretty simple. But due to spin-orbit coupling, and the reason why there's spin-orbit coupling, again, is because we have orbital angular momentum. So you have two magnets there. Either they're lined up or they're not. So if it was 2s, that wouldn't be the case. You only have one magnet, so nothing to line up with. But if you have 2p1, just one electron, its energies are split. Okay, and these are the numbers. So what we can do is we can just plug it straight into that equation. 1/2 HCA J times J plus 1. Just to make sure you're following here. J is 3/2. So 3/2 times 3/2 plus 1. Minus L times L plus 1. Minus 1 times 1 plus 1. minus s times s plus 1. All right. So, geez, this is an ugly mess here. 1/2 HCA. 3/2, let's see, that'd be like 5/2 times 3/2. Yeah, wouldn't that be 15/4? And I can't do stuff in my head. I should be able to do that by now. Okay, so I see 15/4 for that one. Minus, yeah, 2. 2 times -1. And then that's, let's see, 2. 3/2, -3/4. Okay, you see where all that stuff is coming from?
I don't see where it's coming from.
Because like a half plus 1, this is 2/2 plus a half would be 3/2.
Oh.
3/2 times a -1/2
Yeah.
is a -3/4.
I just meant all the L's or all the
Oh,
numbers.
because it's 2p1.
Okay.
So that means little l has to be 1, right? And how'd they get the j's?
Was that from that
Klepsch,
Effect Gordon's?
Klepsch-Gordon coupling. You got to couple them because they're magnets. So how do you get the possible total angular momenta? You have to couple it and follow those funky rules. Okay, Klepsch-Gordon coupling. They're summed down to their difference. So we'll have 2/2 is 4/4. Sorry, 2/2 is 4/2. So 15 minus 4 is 11. Minus 3 would be 8, right? Is that right?
Gordon's series yesterday, we just kept using J.
It didn't really matter. There's all.
Where is the L and the S coming from? 'Cause
That
we
would.
apparently have-
Yesterday we just did practice. Yesterday all we did was practice doing Klepsch-Gordon coupling. We didn't have to. Didn't matter what symbols we used. So what we're trying to illustrate here is that if you have angular momenta, it doesn't couple in the way that if I'm going to have two baseballs flying, how does their linear momentum interact? It's very linear, right? In the way I view it, if a train's going down the railroad tracks and they dump a cart off, right? It just falls off. Well, then the momentum of that train decreases because it lost some mass, right? So that, in a visual sense, that's how I couple linear momenta. But we're not talking about linear momentum. We're talking about angular momentum, a type of momentum that it's really hard to even visualize unless you take that spinning wheel and try to apply some torque to it. It's a very odd type of momentum. So it couples in a very odd sort of way, especially on the microscopic world. So we just kind of got to live with it and follow the rules. Okay. So 11 minus 3 is 8. Okay. So that's kind of where the stuff is coming from.
The P that determined the L and the S,
Mm-hmm.
and the L and the S determined
The J's. Yep. And then the J. Yep. Okay. Let's see. So now notice we no longer have little l, we no longer have small j, no longer small s. They made a huge transition here without really advertising it too much. Now you've got many electrons, not just one anymore. Okay? So now, because now you see capital L, capital S, capital J. And now we're going to start writing some term symbols. So once we'll define, right, the total spin quantum number, the total orbital angular momentum quantum number, the total angular momentum quantum number. We'll define those and give them numbers, and then we'll write term symbols. Okay. So if big L is 0, we're supposed to write a capital S in there for it. if capital L, if the orbital angular momentum quantum number is just 1, we're supposed to write a capital P in for that term symbol. So they're kind of following the hydrogenic orbitals, right? Because remember when little l was 0, we wrote little s orbital. When little l was 1, we wrote it was a p orbital. So they're kind of sticking to that. When the total orbital angular momentum quantum number is 2, capital D. 3 would be probably what? F, capital F. Okay. So this idea of multiplicity now. Let's say we have 2 electrons. Okay. So each electron, a half. Right? So I'm writing little s's. Okay. And we can couple them. To get our total spin quantum number. And how do you couple again? The sum down to their difference, right? So it'd be 1 all the way down to 0. So S could be 1 all the way to 0. So if you want to go back and talk about triplets and those sorts of things, where'd that go? Singlets, triplets. It's the 2s plus 1 idea, right? This one would be a triplet, right? Because 2s plus 1 would be 3. If s is 0, that would give you a what number would you get if s is 0? Just 1. So they call that a singlet. Okay, so all they're saying here is we're triplet. Those 2 electrons are unpaired. Singlet, they're paired up. Okay.
The singlet is paired up?
Mm-hmm. How would you get a doublet? Yeah, just 1 electron. Yeah, because you'd have, if you just have S1 as a half, that's all you got, you'd end up getting S to be 1. That'd be a doublet. All right. Okay.
If S equals a half?
Yeah.
I see.
Yeah, because then 2s plus 1, you get 2. So here are those. The total orbital angular momentum quantum number, capital L. The total spin quantum number, capital S. The total angular momentum quantum number, J. So we're talking about more than one electron now. And then how do we couple these things? Like if you have L equals 2 and L equals 1, so how do you get these capital L, capital J, capital, right? You have to couple. So if you have 1 electron in a D hydrogenic orbital, 1 electron in a P hydrogenic orbital, how do you couple them? Right? Well, you couple the sum down their difference, 3 down to 1. So capital L could be 3, 2, or 1. Okay, and then you can draw their projections. Okay. And again, in the length of their arrow, again, is just that if you're talking about the length of the arrow for capital L, just put in capital L. That's how they get the length, the magnitude, or the length of all those arrows. Okay. Okay. So this is that Russell-Saunders coupling. We called it Clebsch-Gordon. We did a lot of practice on that. Kind of just wrote it all out here, just the sum down to the difference. Okay, and just intervals of 1 in between. Page 379. Let's see what I have on page 379. I didn't scan that.
And now on this that you defined as magnitude, that's something called big L. That's the total.
Magnitude is the length, is the strength of that magnet, right? The strength of the magnetic field. How long you draw the arrow.
But that's going to be all the electrons since you have capital L?
Yes. And there's several possibilities there. Okay. So then there's different types of variations of the coupling. Depends on whether you have heavy atoms or not. And that's kind of what I was looking at for on page 379. But I don't know if you really need to worry about it too much. Okay. So you have, so it's more important for large atoms. Just a general idea. I don't think you need to worry about it too much. Page 379. What's going on page 379? Oh, I should have scanned that. So on page 379, equation 47 is kind of interesting. Whoop, equation 47. There's selection rules there. Large. There's selection rules. How can you go from one transition to another, right? So one of these that I think is curious is they have a bunch of selection rules written there. For example, like delta S is 0, that kind of thing. But this one I thought was really interesting because that orbital angular momentum has to change. That's what this really means to me. So on page 379, equation 47's got a bunch of these little selection rules written for transitions. And the one that catches my eye, it's kind of interesting, is this one. All right, delta little l has to be plus or minus 1. The orbital angular momentum must change. So I don't know, neither really here nor there, but magnetic fields. This is just a unit. A unit of the magnetic moment.
Just out of curiosity, these multiplicities that we keep looking at, the 2x plus 1, is that a direct correlation to what we do in NMRs and stuff every Singlet? Is it those spins and the changing of those spins that adjust that?
For
and doublets and singlets and triplets?
NMR's got that n+1 rule, right? Depends on the chemical environment. The identical magnets, no, that's the right word, but the identical magnets that are around it to do splitting. So that's a different. Yeah, no.
Maybe that's the same terms.
Yeah. So the Zeeman effect. You really don't see a lot of this stuff. You need, in the presence of a magnetic field, you see, remember when we looked through the spectroscope and we saw the lines for different, like the mercury lamp or whatever? Those lines would actually split if you, in the presence of a magnetic field, and they call that the Zeeman effect. See, spectral lines actually split. Okay. So, I don't know. I think they expect you to see a lot out of this stuff when it's really kind of hard. Like, notice the difference between P and S. For S, L is 0. There's no orbital angular momentum. Well, if there's no orbital angular momentum, right, it can't split. Can't split. So I don't know if they're exactly just what is really important in all this is really brought out in the homework, right? But see, there's just some general ideas that the plots and the figures kind of bring out.
What does that Zeeman Effect say? The presence of magnetic field?
Yeah, presence of magnetic field. So you can actually see split lines in those spectral tubes. Anomalous. I don't know. And you're not going to see any of this stuff, but the book brought it up. So that's why I'm just writing it down. So I wouldn't worry about that kind of stuff too much, unless the homework brings it out. So this next part is what I think we want to do for Wednesday. And then on Wednesday we're going to work on this stuff. That's the plan. We'll see how it goes, right? I don't remember how bad this stuff is, or not. Maybe it's nice. Right? Maybe it's nice. So let's take a look at these A exercises, 8, 9, 11, and 16.
I'm sorry, so we'll be turning in handout 13A and do this on Friday, day of test?
Let's see how it goes. Let's see how it goes on Wednesday. All right? Maybe there's just so much there that we break it up into 2 more days. Just see how it goes. Okay. So a lot of these may not be too bad. I don't think they're going to be too bad. Calculate the permitted values of J for a d electron. All right. So how do we do this? All right. If it's a d electron, little l's got to be 2. Okay. So this is just part A. Well, you're coupling orbital angular momentum with what orbital? Sorry, with what type of angular momentum? You're coupling orbital. We only have one angular momenta here. You have to couple it with another type of angular momenta. It was, how do you get total? It's the sum of orbital and s, spin. So you need a number for s.
Just make one up.
You can't make this stuff up.
Okay, I'll just use half.
Use a half, right? It has to be, right? It has to be a half. Okay.
37.
So Clebsch-Gordon coupling, J would be what down to what?
5 halves down to 1.
5 halves all the way down to
1. 5 halves. 3 halves. 1.
5 halves all the way down to 1 half. They sum down to their difference.
Yep. 5 halves, 3 halves, 1 half.
What's the bottom number? It's not a half.
Oh, no, my bad. Just 3 halves.
3 halves. All right. Okay. Anything in between? No. So you can do F, right? Let's jump down to number 9.
Oh, that was it for...
Well, you can figure that out. That's all you do, right?
You just do that for that one and B?
And the same thing for B, but now you have an F electron.
Do I use a half for S for B also?
Do you have any choice?
I don't know.
Yeah, you do. What is the only possible value for this, for spin, for little s?
Is it
Has to be a half or negative a half, but we don't. It's absolute values. We always just pick spin up. Okay. Electron in different states of an atom is known to have J is 3 halves and a half. What is the orbital angular momentum quantum number in each case? All right. If the total angular momentum quantum number is 3 halves and a half, what does little l have to be? That's what they're asking. How'd they get these J's in the first place?
Oh, you're adding the S and the L.
Adding the S and the L.
Yeah, the total has to be this, and the difference has to be half.
Yeah.
Yeah.
Yeah. So little L has to be 1. Has to be. Because S is fixed. So little L has to be 1. See, man, you're flying through this stuff. Maybe I said it wrong. Maybe we're going all the way through this stuff.
The rest of them.
What information does the term symbol provide about the angular momentum of the atom? Okay. So remember, there's 3 types of angular momentum. So pretty much all it wants you to do is find these. Remember the expression for term symbols. Otherwise, this might be kind of hard. Where'd it go? How do we write term symbols? Here it is. 2s plus 1 Lj. That might help you. What does J have to be? I told you the term symbol. So Pablo, what does J have to be? 2. All right. What does L have to be? 2. What does S have to be? 0. All right.
How'd you figure that out?
Because you have to know this. If you don't know this, and then you're out of luck.
Oh.
Right? And you just match it up.
Okay, cool. All right.
Okay.
My mind wanders.
Suppose that an atom has 2 electrons. We're doing part A. 2 electrons in different orbitals. What are the possible values for the total spin quantum number? What is the letter, the variable we're supposed to be writing for this? Total spin quantum number. You're supposed to be writing now, capital S. Very good. Notation's going to be everything in this to help you out. Okay. So that means you're coupling what to get capital S here in this part A? You have to be coupling
2 S's.
2 small case S's, right? They're individual electrons, so you should write little s. How many are there? 2. So I'll have a little s1 and a little s2. And what do I put in for those? Whether they don't really have a possible. They only have one choice for a number, half. So couple them, and you'll get your answers. How about part B? What changes? Now you have little s1, little s2, and little s3, and they're all a half, right? So there, you go back to that. If you don't remember how to couple 3, you might want to go back and review that. We coupled 3 things. How about calculate the permitted values of J for a p electron?
L plus S.
Yeah, so just figure out what L and S are and then couple them. So I don't think this stuff is too bad, right? Hmm?
Yeah, okay, so I can just pick an L and an S.
Can you pick any L?
No.
Little L has to be what?
1.
What does S have to be?
1/2.
1/2. And I should even be more careful. Be anal with your notation here. How many electrons are there? How many electrons are there?
2 in each one.
A p electron.
6.
So just one.
A p electron. So you're gonna write little L1 is 1, little S1 is a half. So you don't have to be coupling all these different L's to get what L is. No, and plus they gave you a hint here. It's smaller case J. So all your coupling is L is 1, S is a half to get your answers. Okay. Same thing with part B. How about number 9?
That's tricky, so we're going to do A to B's.
Yeah.
What are the allowed total angular momentum quantum numbers? Composite system with J1 is 5, J2 is 3. Hint, see page 379. What the heck? Why do you need a hint for this?
No, we just do what we've always been doing.
Yeah, just do what we've always been doing. I don't know why you need a hint for that. Kind of odd. Should cross that out. You don't. That's just confusing. There's nothing special about that.
So mark out the hint.
Yeah, we would need it.
Okay. So we go from 8 to 2,
Exactly.
and then what? And then that's it. We just give the M's to J's or what?
Again,
Oh, do we have to do the square root of J times J plus 1?
Now-
H bar for all of us?
what you're trying to do is memorize something. You don't memorize in any of these problems. You provide what they want, right? Follow the mathematical steps or the rules to get what they want. Nothing extra. Nothing extra, right? What are the allowed total angular momentum quantum numbers? So what symbol is just like going back to general chemistry and they want you to use ideal gas law, calculate the pressure. What you did first is you wrote big P equals question mark. So what would you do here in this one first?
Big J.
Big J equals question mark. Do you look for M sub J?
No.
No. Do you draw arrows and projections?
Yeah.
Right? That's it. How do you get big J? Look at what they gave you.
Oh, okay.
You're coupling how many things? Just 2. And how do you couple? The sum down to their difference.
Okay, so
Okay.
the arrows are projections when you see the word magnitude.
Or they ask for it,
If you
right?
ask for the magnitude of
If they ask you for projections, then you should give them projections.
Come on, we give the applications. You have projections.
I was just like, how do I know whether I put L in there or J? I guess J stands for the angular momentum, right? It could be the different L's. It could be 0, 1, 2, 3, 4.
They say total.
Let's say total now.
Know this. Know what J is called. It goes back to your notes. Definitely know this. Where'd it go? Right here. Definitely know this. Do the names change if there's 1 electron? Do the names change if there's 1 electron?
No, they just get this low.
The names don't change. What changes?
The
The case. Exactly. The names don't change.
For capitals for many electrons.
Capitals for more than 1 electron. Yep. Okay. So this stuff isn't. You can do this. So come by. I'll be glad to help you out.
Well,
Okay.
we get to do those 2.
I'm not sure where we were supposed to have stopped here.
13.9.
I only have 8 problems in the first.
Where did this go? Maybe we went too far. We're supposed to go to B exercises 8, 11, 20. Yeah.
Go some more.
So, and then, I mean, there's no reason why you couldn't keep going here, but we'll work on this in class on Wednesday. But you'll get more out of it, I think, if you can blow through all this stuff and start working on it. You'll have questions then on what we're going to do in class.
Do you want us to start
Okay.
on that handout or the handout?
I suggest not starting on the handout.
Just actual homework?
Start do this.
We're-
Okay.
Okay, but you're going to give us the
Yeah, the further you get, even on the handout, the further you get on all this stuff, the better off you'll be for Wednesday.
So for Wednesday, only.
Wednesday, this is what you have to turn in, and I suggest starting this because this stuff is going so fast. So I suggest getting started on Wednesday stuff because then you can ask some questions in class when we're working on it.